Hello, welcome back. This is Math 1530, College Algebra, and today we're going to look at quadratic functions. So the first thing we'll deal with are the graphs. So graphs of the quadratics, these things y equal ax squared plus bx plus c. There's two different versions that we look at in this class. There is the kind of concave up is what they call it version, and then this thing will have an axis of symmetry going through what's called the vertex. Okay, so this point right here is the vertex, and usually we give the vertex the coordinate h comma k. Don't ask me why, but it just is that way. And again, this line right here, this dashed line, is the axis of symmetry. And it goes through the line x equals h. Okay, so the equation of the axis of symmetry is x equals h. What else? What else can we tell you about this? Well, one last thing. In this case, the leading coefficient of the quadratic, a, as you can see there's an a in the y equals ax squared plus bx plus c, is greater than 0. That's how you know it's concave up, as opposed to, drum roll, concave down. Okay, so the other type is concave down. And here is our picture with the vertex now on the top. Okay, and we often use these things for doing maximization and minimization. So if it's concave up, the first case, we can minimize that thing. We just look for the vertex. If it's concave up or concave down, the second case, we can maximize it by finding the vertex, right? Again, the vertex is given location h comma k. The axis of symmetry is going right through it. And it's located at x equals h, and the leading coefficient this time is negative. Okay, there's two forms for the quadratic at this point. There will be the standard form, which I just gave you here. Okay, and also then, well, I guess they don't call that the standard form, do they? I wonder what they call it. I don't know. I guess it doesn't have a name. That's so sad. Well, okay. So they used to call this other form the vertex form, and then they called that guy that I just boxed in the standard form, but I guess they changed it. Things are always changing. Don't get old, folks. Right? So anyways, let's look at this thing they're calling the standard form of the quadratic. And the advantage of this form, and why I used to call it vertex form, is because you can read the vertex directly off of the equation for the function. Okay? Clearly a cannot be 0, it would just be a horizontal line. Okay, so the great thing about this is you can read the vertex off of the equation. The vertex is the coordinate h comma k. You just take the opposite sign of the thing inside, this x minus h, or you could think in terms of shifts, right? If it's minus h, it's shifting over to the right. A plus k on the outside makes it go up, right? So you can think of it that way too, but most people don't. I don't know. Anyways, we're going to be expected to graph these things. So first, I have this procedure I'd like you to outline when you graph these. Especially, I guess for my math lab, they'll sort of walk you through it. So anyways, here's my procedure, right? So first I identify the leading coefficient, and that gives me an idea of what the graph looks like, right? If a is less than 0, it's a sad face. If a is greater than 0, it's a happy face. Right? Secondly, then, I identify the vertex. The vertex is h comma k. I just read that off the equation. Thirdly, I'm going to get the x and y intercepts. For the x-intercept, you let y equals 0. For the y-intercept, you let x equals 0. Fourthly, I'm going to state the domain and range. And then the domain is always all real numbers. So that's going to be easy. The domain is always negative infinity to infinity. The range is a little bit harder, but you could still kind of figure it out without even looking at the graph. Okay, the range there's two cases, right? So if it's concave down, it tells you the range will go from negative infinity to the k value from the vertex. If it's concave up, that tells you the range is going from the k value of the vertex to infinity. Okay? And it's just, think about the graph. If you have a graph and let's say it's concave up, and here's my vertex at h comma k. This point on the y-axis is k, right? So if I smushed my graph using my trash compactor against the y-axis, right, it would be smushed from k to infinity, which is the range that I was talking about right here. Okay, so you can always just kind of figure that out without looking at the graph. Okay, so number 5 then, the axis of symmetry is kind of also what I'm after. Okay, so let's take a look at these guys. I want to, go through that 5-step process, and let's look at an example. So we have f of x equals x minus 3 squared plus 2. Okay? And so first off, I want to identify whether it's, all right, so the a value in this case is what, it's whatever's in front of those parentheses. In this case, it's 1, which is greater than 0, which tells me it's a happy face. Okay. Secondly, then the vertex, I can just read that off. It's 3 comma 2. Okay. And again, if you think in terms of shifting, it's going to take our quadratic y equals x squared and then shift this direction right by 3, and then it's going to go up 2. Right? And that gives you basically the location of the vertex. So I go 1, 2, 3, and then up 2, and that point is 3 comma 2. Okay? So that's one way to remember it. Or you just take the opposite sign of the first guy and keep the same sign of the second. Right? Okay. X and y intercepts. So for the x-intercept, you let y equals 0. So I have 0 equals x minus 3 squared plus 2. I can kind of use the square root property to solve this. So move the 2 to the other side, negative 2 here. Square root property says x minus 3 then is equal to plus or minus square root of negative 2. Oh, so there's not going to be an x-intercept because it's imaginary. And we can't, well, at this point, you can graph imaginary numbers, but we don't. Okay. All right, so there's no x-intercept. Okay, y-intercept. For the y-intercept, you let x equal 0. So we have y equaling 0 minus 3 squared plus 2. So y equals negative 3 squared plus 2. So y equals 9 plus 2. So y equals 11. So I get 0, 11 as my y-intercept. What else? Domain and range. Okay, so for the domain is always all real numbers. And then the range, because it's happy face, it'll go from the bottom up, right? So the bottom is located at 2. I'm just taking the y coordinate here. And then it's going to go to infinity. And then finally, the axis of symmetry. The axis of symmetry is always x equals the x coordinate of the vertex. So it's always x equals h. Right, so back there, you just borrow, for the range, you're borrowing k from the vertex. For the domain, or sorry, for the axis of symmetry, you're borrowing h. Okay. So finally then, our axis of symmetry, x equals 3. Okay. Okay, and then finally you can graph the thing. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You know there's a y-intercept there. The vertex is at 1, 2, 3, 1, 2. There's the axis of symmetry, goes right through it. And then if you can draw half of it, just reflect that half around the axis of symmetry, and you should be good to go. Okay, there it is. Yay. All right, next. This one is given not in standard form, but you can remedy that, okay, if you're ambitious enough to do so. So f of x equals 2x squared minus 7x minus 4. Okay. And we want to put it into our nice form, right? So what do you have to do? You have to complete the square. So f of x equals, first off, I have to factor out a 2 from here, so x squared minus 7 halves x, and then I'm going to be adding something in. Right? But if I add something in, I have to immediately subtract it, and I'm going to be multiplying it by 2 as I subtract, then minus 4. Okay. Because if you add something in, and that slot inside the parentheses, it's actually, what you've added in is that thing, but then multiplied by 2, right? To get back to the original statement, you have this thing that you've added in, but it's actually multiplied by 2, so you have to kind of immediately remove it, minus 2 times whatever that thing is. Okay, so that's my sort of rationalization for all that. Okay, so anyways, the thing that we add in is always b all over 2 squared. Negative 7 halves divided by 2 is the same as negative 7 halves times 1 half. Then I have to square that. So I'll have negative 7 fourths squared, which will be 49 sixteenths. Okay, so I'm adding 49 sixteenths here and putting it right here as well. Okay, so let's now clean that up a bit. So f of x will equal 2 times x minus 7 fourths squared minus this thing, 49 eighths. 4 is the same as 4 over 1. And then I can find a common denominator and multiply top and bottom by 8. Okay, so that's going to be minus 32 eighths. And so finally, f of x will be 2 times x minus 7 fourths squared minus 9, 10, 11, carry the 1, 7, 8, t1 eighths. Blah, right? It's a real mess. Okay, so anyways, now we can go through the 5-step process of getting all of our information. And first, the a value is 2. That is greater than 0. That tells me it's a happy face. Secondly, the vertex, can read that off. That's just going to be 7 fourths, comma, negative 81 eighths. And it's probably a good idea to get like a decimal approximation for those points. The first one is 1.75. The second one is negative 10.125. Just it's easier for graphing. Okay. Then I need my x and y intercepts. So for the x-intercept, you're going to let y be 0. And I'm going to go back to 2x squared minus 7x minus 4. 2x squared minus 7x minus 4 equals 0. Gee whiz. Do I have to use a quadratic on that? Did I even write it properly? 2x squared minus 7x minus 4. Hopefully there's no solutions, right? Let's take a look. So it's x equals negative 7 plus square root b squared, minus 4 times a times c. Oh well, over 4. 1630, this 4 times 4 is 16, times 2 is 32, plus 49. 9, 10, 11, carry the 1, it's 81. So I get 7 plus or minus square root 81. Well, that kind of works out. Is 7 plus or minus 9 over 4. So we're getting 7 fourths plus 9 fourths, which is 16 fourths, which is 4. Or the other intercept, 7 minus 9 fourths, which is negative 2 fourths, which is negative 1 half. Okay, so we got those x-intercepts. And then for the y-intercepts, you're letting x equals 0, right? So you have y equals, this is easy, if you plug zeros into the 2x squared minus 7x minus 4, it'll just be minus 4. Whew. Okay, domain and range is always kind of simple because you just use the vertex. So for the domain is always just negative infinity to infinity. The range, then, because it's concave up, or happy face, you're starting at negative 81/8 and going to infinity. The axis of symmetry is based off the 7/4, so x equals 7/4. And finally, we can go ahead and graph the thing. Jeez. Okay, so it's going to be a little 1, 2, 3, 4, 1. So the x-intercepts, the y-intercept down at 1, 2, 3, 4. And then the vertex is at negative 10 something. 4, 5, 6, 7, 8, 9, 10 point something. And then 1.75 is in here. And then the axis of symmetry is at 7/4, so 1.75 as well. And then you can draw it in. Okay. Look, so some of them can get pretty nasty when you start dealing with fractions and all that stuff. A little easier when you're graphing is just go ahead and convert that into decimals. Okay. Okay. It's kind of time consuming. It's not hard. It's kind of like it's an incredible thing if you think about it. This equation right here, if we unpacked it. Okay, I didn't need a book or anything, but I was able to get all of this information from just that equation. And that's the power of math. You get these couple lines of symbols, and you can unpack it into an encyclopedia. It's just a very, very powerful thing. Okay. So that was graphing what they're calling the standard form, which I used to call vertex form. So now we want to move into, well, let's say I want to graph this thing without converting and completing the square and all that jazz. Okay, so this thing I just pointed to in the box, which we don't have a name for, right? So section 2, doing the form y equals ax squared plus bx plus c. So for this form, you kind of need to have a vertex formula. Okay, so graphing, and again, I'm going to give you a kind of a process, except there's that vertex process a little harder. So first, again, you're thinking if a, the leading coefficient, is greater than 0, then it's a happy face. If a is less than 0, it's a sad face. Secondly, the vertex. Now this is the hard part, the vertex h, comma, k. It's not hard, but you have to memorize something. For me, I hate memorizing, so it's hard for me. Maybe not for you. H equals negative b all over 2a, and then k will equal f of negative b over 2a. So you basically just take the x vertex and plug it into the equation, and then that will give you the y vertex. Okay, so that's the worst part. And then you get the x and y intercept. Then we will get our domain and range, and again, the domain is always going to be negative infinity to infinity. The range will be, this if concave up, then it's going to go from the y coordinate of the vertex to infinity. If it's concave down, it goes from negative infinity to the y coordinate of the vertex. And then finally, the axis of symmetry is x equals h, okay, for the axis of symmetry. Okay, okie dokie. So let's take a look at maybe one or two of those. And again, these can get kind of annoying if the vertex gets out of hand, which it often does. Even more annoying when you're dealing with roots, square roots, and your intercepts. Just try to keep a level head about things. X squared minus 2x minus 15. Okay, so let's go through this, right? So first, a is greater than 0. That tells me it's a happy face. Secondly, then the vertex. Right? Okay, so now we need a formula. So h is equal to negative b, so b is negative 2, all over 2 times a, and a is 1. So negative 2 is positive 2, 2 times 1 is 2, 2 over 2 is 1. Then you take that value, this h value, and plug it into f of x, right? Because clearly that's just how you do your tables, right? Once you get that output, you know, when you're graphing things and you do that table, if they give you an x-coordinate, to get the y-coordinate, you just plug it into the formula, right? And that's what you're doing here. You're just getting the corresponding y value. So if you plug in 1, you get 1 squared minus 2 times 1 minus 15. 1 squared minus 2 is negative 1 minus 15, so it's negative 16. Okay, x and y intercepts, so the x-intercept, you let y equal 0. Okay. Sometimes you have to use quadratic. I think this one's going to be easy though. Yeah, so x minus 5, x plus 3 is 0, so x equals 5 or x equals negative 3. For your y-intercept, you know, let x equal 0, so in this case y will be negative 15. And then domain and range. Domain is always negative infinity to infinity. The range, going from negative 16 to infinity. And then finally the axis of symmetry is x equals 1. And then we can go ahead and graph it. I need to go down kind of far. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I think either go. Yeah, 1, negative 16 was the vertex. Okay. 5, 1, 2, 3, 4, 5. That's one of the intercepts, and then negative 3 was another one. You have a y-intercept at negative 15 is down here. The axis of symmetry, x equals 1. And then you can go ahead and connect the dots and you're ready to go. Okay. Let's look at some applications. So if you can model whatever you're working with a parabola, you can maximize it because the vertex is either going to be the max. If it's a sad face, it's a min. If it's a happy face, okay. So clearly, in this previous example, that vertex would be the location of a minimum value. Okay. So sure, let's write that out. So section 3, applications. So first, if your a value is greater than 0, your function f has a min value at x equals negative b all over 2a, right? The x-coordinate of the vertex. That's not the actual min. That's just the location of the min. The min, then, is f of that negative b over 2a, the y value of the vertex. And then clearly, secondly, if you have a sad face, the function has a maximum, and its location is x equals negative b over 2a. And then finally, the maximum value is f of negative b over 2a. Okay, so just a small detail, the difference between the x and the y coordinates. The x is the position, the y is the actual value of the max or min. Okay, so let's try one. In physics, they use these quadratics to model projectile motion. Okay, so I think this one is on shot put, somebody throwing a shot put, and the projectile's motion can be modeled with this parabola, negative 0.04x squared plus 2.1x plus 6.1, where the y value, g of x, tells the height in feet of the projectile. And then the x value tells the horizontal distance from the thrower. Okay. Okay, so the first question, part A, they want to know what's the maximum height of the shot put. Okay. Okay, so in order to get this, we need the y coordinate of the vertex. So first I need to get the x coordinate, h, so that's negative b, 2.1, all over 2 times a, negative 0.04. If you put that in your calculator, you'll get 26.25. And then that's the location, right? 26 feet away from the shot put thrower is when the shot put thing reaches its maximum height. Okay, but that's not the maximum height. The maximum height is you get that by plugging that number back into the formula, 26.25 into our formula, so that's negative 0.04 times 26.25 squared plus 2.1 times 26.25 plus 6.1. Okay, and then I calculated that already. It's 33.6625 feet. Okay, so the maximum height then of the shot put is not 26.25 feet. It's 33.6625 feet. If you want to include the 26.25, that's where it occurs. Okay, the max height of the shot put occurs 26.25 feet away from the thrower, or whatever they call the person. Okay, what's next? Next they want to know the distance of the throw. So if you think about this visually, we have a sad face scenario going on, and the vertex is at 2633, so it's in the first quadrant. Okay, so our vertex is out here somewhere, and it's an upside down parabola, right? It's a sad face. Okay, so there's, if it's modeling the shot put throw, there's the place where it hits the ground is going to be out here somewhere. Okay, this other one is kind of where it started. Actually, you'll see later that the shot puts with, what is it, the y-intercept is actually up here. Okay, so a more realistic view would be this, without this part of it. Okay, so when time is 0, the shot put is actually 6.1 feet. You can see that in the formula. If you put in 0 for x, this will be 0, this will be 0, but then you'll go off to 6.1. It's probably the height of the person who threw it, right? Okay, so anyways, we're looking for this point. And what are the coordinates on this point? Well, it's x comma something, y, right? But what is the y value? Well, when it hits right here, that's the x-intercept. So y must be equal to 0. So to find the distance of the throw, what we do is put 0 in for y and solve. Okay, so I have then 0 equals negative 0.04x squared plus 2.1x plus 6.1. Okay, and then we could dump that into our quadratic formula. I like to get rid of all of the decimals and all that stuff and get a positive leading coefficient. So first I'm going to multiply everything by negative 100. Okay, so 0 will equal 4x squared minus 210x plus minus 610. Okay, so I just multiply both sides by negative 100. Then I could see that these guys are all divisible by 2, so I'm going to divide everything by 2 or multiply by both sides by 1/2. Okay, so I end up with 2x squared minus 105x minus 305. Okay, then I'm just going to go ahead to the quadratic. I don't see any possibility of me factoring that. So I'll have negative b, which is negative 105, which is 105, plus or minus the square root of, and I don't want the minus one, right? I just want the plus version, but so we can kind of exclude the minus, because the minus would give me the other place, the one I'm not interested in, this place right here. Okay, okay, so anyways, b squared, so 105 squared minus 4 times a times c. And it's not necessary to even do all these, like multiplying by negative 100. You could have used this thing I'm circling and just use those as your a, b, and c in the formula. I just did this in case I could factor it. I'd rather factor than do the quadratic. But if you just want to jump to the quadratic, go ahead. Okay, so down below it's 2 times a, which is 4. And if you put that in your calculator, which I did earlier, you'll get about 55.26 feet, okay, as the distance of the shot put throw. Okay. I guess the last question, and then we'll call it quits, is the initial height. And if you look at the formula, the initial height is basically times 0. When the horizontal distance is 0, when the shot put is basically in the hands of the thrower. So you could put in x equals 0 and evaluate. Right? So g of 0 is going to be negative 0.04 times 0 squared plus 2.1 times 0 plus 6.1. The first two terms will just end up being 0, and you're left with 6.1, which seems like a reasonable height for somebody who's like an Olympic person throwing shot put. Okay, that's about it. We'll just leave it there. And again, thanks for watching, and we'll see you next time. Okay.